Hi, good morning. Buenos días. If this falls in my laptop, it's going to be really funny. Yeah. Hello, everyone. Welcome to DevOps Barcelona. I'm Ines, and this is Patrick, and we're both honored to kick things off this morning. I'm a VP of Engineering at Fastly, and Patrick is a distinguished engineer at Fastly. If you don't know what Fastly is, I will tell you. It's relevant to our story.
Fastly is an edge computing platform where we help to make the internet a better place, where all experiences are fast, safe, and engaging. And what this really means in reality is that we're a global network that helps deliver the internet experiences for some of the world's largest companies. And that equates to 1.8 trillion requests a day on a network that serves over 377 terabits a second of data over our capacity. And so really what that means is that we've likely helped to serve a lot of the internet experiences that you've had on your devices already this morning.
All right, so as Patrick mentioned, Fastly has built one of the world's largest edge computing platform. When I started at Fastly almost 10 years ago, the numbers that I kept seeing seemed ridiculous then, and then right now, like they seem so small. And every year, just like the wave of growth keeps just eradicating the numbers that would seem large the year before. So we're here to give you a behind-the-scenes view into what it takes to make a platform like ours possible at global scale. We've learned many lessons evolving it, and today we'd like to tell you how we do it, share the patterns that have worked for us, and what gets tricky when you're architecting for scale like we do. Hopefully, some of the lessons that we've learned are going to be helpful to you, because the nice thing is that when you have a site that is emerging, you have some load. But if you get very successful, you get the joy and also the pain of having to do more work. And that is kind of like a thing of life now. So the more successful you are, congratulations. The more work that you have.
The more pain. OK, so let's dig into it. There are many industry practices around building good software, writing good code. Things like writing unit tests, continuous integration, continuous deployment, automation, using the cloud. Many of these things are likely practices that all of you do on a daily basis, right? And probably some of the reasons why you've come to a conference like this to learn and speak more about those practices. And these are also things that we do at Fastly, right? But what we realized is that that wasn't enough for us, and we needed a set of guiding architecture principles, a rubric or a checklist that we could use and that we've learned from years of building large distributed systems, and we could use that checklist every time we're thinking about adding or extending or changing the platform. And that's where the Fastly architecture principles come in. And I'm excited that we want to show you them today. We rarely talk about them externally at Fastly. And these are principles that can grow and evolve with us as we grow and scale the platform. So let's have a look at them. There's 8 of them. Availability over everything. 0, 1, infinity. Scale horizontally. Safety before features. Customer data is their own. One network, all features everywhere. One of my favorites, fix and expand the internet ecosystem. Limit only for safety and availability. And build Fastly with Fastly, which is one of the key themes of our talk today. Now, I would love to be able to go into all of them in detail today and explain why we came to that principle and how we've used it and adapted it, but unfortunately, we don't have enough time to do that.
It'll be a very long talk.
Inez and I have chosen like 3 or 4 of our favorite ones, and we're going to use them to navigate us through this talk today. Each one of the examples, we're going to choose on how we came to that, what we've learned from doing it, but importantly, the challenges that have also come by applying that principle at scale and the tensions they have with each other.
All right, so let's dig in. I have to say that I almost had an image of you with the 10 architecture, well, the 8 architectural principles as if you were Moses.
I've got them tattooed.
Yeah, I know, they would have been great. So let's dig in. Sorry for the digression. The first principle that we want to discuss is customers' data is their own. Customers trust us with their data, and we take this responsibility very seriously. We take this responsibility so seriously that we don't want to keep anything that we don't have to. We only store what is necessary to operate the platform, and we follow very strong data governance policies. So this is a great principle, right? It's us honoring our customers' trust and being very intentional about customer data. But let's explore two ways in which this principle gets complicated or gets tricky at scale. It can be difficult to know when to measure and retain data. Data is power, so more data has to be more power, right?
Yeah.
No.
Oh.
No, unfortunately, no, Patrick. At scale, you still want to measure what is absolutely necessary and not more. Why is that? Because basically, more data means more problems. Yeah. More cost to process it, more cost to store it, query it, even warehousing it is expensive. So over the years, we've been very deliberate about what we choose to retain and what we don't. We drew a very hard line, and we kept it. Another challenge with this principle is that we want to give customers full control over their service configuration, but sometimes when pursuing a goal, we can take things a little bit too far, like when we expose our architecture in our APIs. We'll give you some examples to illustrate these two challenges and these points, and then discuss the way in which we solve these problems and the methodology we follow. Speaking about methodologies, I will share you my methodology. And usually when I'm pondering life's hard questions, my method is very simple. I turn to Patrick and ask him the answers. So let's all follow it along. Patrick, what can we do to follow this principle better at scale?
Oh, thanks. I thought you'd never ask. She really does do that as well. So as the principle states, customer data is their own. And therefore, historically, the way that we interpreted this principle at Fastly is that we would never store any customer data which we shouldn't have access to or want to, such as, say, the customer's request logs. But this meant that it was challenging for customers when they needed to debug, troubleshoot, react to an incident, or investigate, for instance, like a DDoS attack. Because they didn't have the logs, they'd come and ask us for them, and we didn't store them because of the principle, and so we wouldn't even be able to help them because we weren't even storing their request logs. Now, while that's good because we can't have legal situations where people come and ask us for data that they shouldn't have access to, it's also caused a friction to customers. And so instead, what we told them to do was to use our log streaming capability. This allows you to stream your full request volume coming out of your edge services to any third-party destination of your choice. That could be S3, Splunk, BigQuery, New Relic, etc.
But it still meant that we didn't have access to them, because if you're a customer, you can send it to your S3 log, but if you need us to help you debug something, we don't have access to your S3 logs.
Right, and so with that flexibility, it was great for the customer because they could send it wherever they owned their own data. Also came quite a lot of complexity. They would have to set up that infrastructure themselves, but importantly, significant cloud cost, especially at the scale that some of our customers are, that they're having to pay for the storage costs of that. More data, more problems, as Ines said, right? So we heard repeatedly from customers that while it's fine in principle that you don't store we don't store their data, actually, there's sometimes they would prefer it if we did. And that's where the rule now is that we don't store any customer data unless they specifically opt in and allow us to. And the refinement of that principle then allowed us to actually build a whole new suite of products, such as this one, which is Insights. And this stores and visualizes request data for our customers, removing that cost and complexity that came with them having to set up the pipeline themselves. But the cool thing about this product, and something that we're going to talk about a lot today, is that it was built by simply leveraging a lot of the platform primitives that we already had in place on the platform. And when a customer enables Insights, they stream their request logs to their own place, but we also use that same log streaming and aggregation pipeline, just as the customer would, to stream it to our own data storage platform. We then expose those metrics in our API and built a UI on top of it. So a customer is also capable of building this exact same pipeline, that exact same dashboard, but we've just done it for them, and we've taken away that cost and complexity for them. We also remove all of the personally identifiable information, or the PII. In ingest point, we scrub that data so they don't have to worry about it.
And this is, again, us not keeping data that we don't have to. And also, it has a nice benefit because we don't make our customers have to do this work of just sanitizing and removing this data from their logs.
So you can see that we're both adhering to, while tweaking the architecture principle that we set out from the beginning, whilst also leveraging platform components. An example where this principle has been challenging for us, though, is in a technology that we call shielding. Shielding allows a customer to designate one of our data centers, or a point of presence, we'll probably call them from now on, to act as a shield for their origin. And so any other request coming from any other of the points of the POPs or the data centers around the globe all have to flow through that shield before they go to the origin. The reason why we do this is it significantly improves the cache hit ratio for the cache storage for your HTTP objects, while also reducing the origin offload, because now only one point of presence is going to your origin rather than hundreds. But as we scaled the platform, we've started to add a lot more POPs, because that's good. We've had customer growth, company growth, and sometimes we have to decommission those POPs. We have to move them, we have to merge them, we have to take machines offline. And because customers own their own data, they own their own configuration, and therefore they owned the POP definition that should be their shield. And so this caused friction and intervention from Fastly when I had to come and say to Inez, it's like, we are now decommissioning the Barcelona POP, we're moving it to the Madrid POP. That's not a good thing for you to hear of the operators of those customers that we have to move them. We're causing intervention. And so the lesson that we took from this principle is that we took it too far. Because customers, we wanted them to own their data, we gave them that granular control, but what we've done is we've actually exposed our physical network architecture in our API. We've moved a low abstraction to a high abstraction, and we've learned that that's the wrong thing.
Yeah. So the reason that it was also a wrong thing is because it wasn't just like removing them or just merging them. It was also growing them. And at scale, we do that a lot. So as we were thinking about this problem and this tax that we were imposing on our customers, we realized that the platform should solve this for them. Because a rare event, like a hard drive failing in a server, may become rare when you have few of them, but at scale, it becomes a daily occurrence. So why bother customers with these events that are just completely ours to do at all? So to fix this issue, what we did was introduce a feature that we call smart shielding. Instead of selecting a shield with a specific POP, as Patrick mentioned to us, now you're able to reference a logical region. In here, in this example, you have, look, I was told that I had one of these ones, so I wanted to use it. You have Asia East in here, and this just refers to like Narita or Tokyo. So before, you would have had to select one specific one as your shield, but in here, I can just call it a full logical region. So this is really, really cool. It's clearly a better way to give customers control over their configuration data without removing any functionality or impacting their cache hit ratio. Instead, what we ended up removing is toil and friction for our operators. We like to learn from our mistakes, especially the painful one, and this one was very difficult to course correct. Mostly because every time that we wanted to make changes, we had to go and to our customers because it impacted them every time we wanted to do anything. So what we did is like we've internalized this lesson. We're looking for places where we're exposing too much of our internal architecture in our products, and we're bringing these patterns to all of them, to all of the places that can take advantage of a similar improvement.
So, for example, another place where we've reached for smart abstractions to solve a problem where we've leaked information is with data compliance. And as the principle dictated, is that we follow strong data governance policies. And a lot of our customers rely on us for doing that, because customer data is not only their own, it's normally always governed by compliance and regulation laws in the countries that the customers operate in. So it's their own, but they needed granular control over where the data actually lives and traverses through our network so that they can comply to the regulations in their regions. So this is why we built the compliance regions technology. And now customers can choose exactly the region, which is the higher level abstraction, rather than just a POP that their traffic can be served from. And now the packets which land on an out-of-region POP For instance, in this example, London, which unfortunately isn't in Europe anymore.
Whose fault is that, Patrick? I don't know.
And this customer wants their packets to only be served in Europe, so we will forward the packets to the Amsterdam data center where the TLS is decrypted. And so the cool thing about this is because we're just forwarding the packets, the TLS certificate and handshake will not happen in London, it will happen within region. And we only store the certificates for that customer within region, and it won't even get encrypted in London, which I think is pretty cool.
Ah. All right, so that was customers' data is their own, and we saw a few examples of what gets challenging and how we have corrected some of the mistakes that we made along the way while trying to follow this principle. So the next principle we want to share is 0-1 infinity. And this is one of Patrick's favorite, and the one that he and I argue over the most. When we were preparing for this talk, the conference organizers told us that we're not allowed to fight each other on stage, so we're going to do our best to not do that. But I will tell you why it's something that causes discussion among us in a minute. This principle describes our approach to scaling our platform. In a nutshell, what we want to do is avoid architectural decisions that make it harder to meet new growth. Let me give you a trivial example. When you're small, it may be that you have one component, like say, for example, a database. Scaling up a singleton, you can always make this database bigger, but it will only take you so far. You want to keep in mind the option of horizontal growth when architecting your platform, because you're going to have to. At some point, one point or another, you're definitely going to have to grab this singleton and turn it into something that can be horizontally scalable.
So this rule may sound familiar to many of you in the room, because it's a well-known computer science principle coined by the computer scientist William van der Pol. And it stated that arbitrary limits on the number of a particular type of data structure, so an arbitrary limit, let's say you're only allowed to have 6 of these things, shouldn't be allowed. And instead, either the entity shouldn't be forbidden completely, only one of those entities should be allowed, or any infinite number of those entities. And this is really one of my favorite principles, and the more you think about it, the more it guides your practice, it allows you to build systems that scale infinitely. And this is the 0-1 infinity rule.
All right, that was great, Patrick, but let's explore what makes this principle challenging to follow at scale. The closer the data is to you, the fastest you can make a decision. But as you grow, you start hitting resource limits, I/O, bandwidth, and memory. More data, more problems, thing again. The more important thing is that it can be difficult to predict when the speed of your decision-making will be impacted by resource starvation. You won't know when it happens until it happens. An unbounded API may be OK today when you're small, but at scale, it may cause you a lot of problems, so it's important to pick the right system primitives. Another side of this coin is when you try to architect for infinite scalability. The way the principle is phrased gives me a lot of tension with it, because it often sends engineers into the land of impossible quests. Clearly, nobody here has done one of those before, right? Never. We've never done this. But what happens to me is that I find myself saying the same thing over and over, and I will model this to you. Patrick, you don't have to scale infinitely every POC that you make.
But I thought I had. The rule told me I have to.
No, actually, no. You want to scale your systems incrementally.
That makes more sense.
It never goes as simple. You will get usually a back and forth, and somebody feels very passionate. We just try to give you the sanitized version because we were told that we have to. So the reason here is that there's a push and pull about making the correct architectural trade-off, and more importantly, is at the correct time. So this is why he and I just spend a lot of our time thinking is that when is the correct time to just change an abstraction or just make a different decision. Our systems need to do their function well, but in our experience, it's best to address any scalability issues when they present themselves. And what we need to do is also be super careful about baking in any assumptions that rely on vertical scaling. So let's do it again and put Patrick on the spot and and ask him, just Patrick, how can we follow this principle better? How can we refine this?
Why, thank you for asking. I think a really good example of where we've got this right, and this is actually part of the foundations of Fastly, and how we architect for 0-1 infinity, is are HTTP caching and delivery, which is at the core of our product. But specifically, it's the way that we built and designed this system from day one that has allowed us to scale infinitely, and is actually one of the key differentiators for other solutions on the market. And it's because this design allows us to scale linearly while still maintaining a best-in-class cache hit ratio. And that's because the way that our HTTP objects are cached are only ever stored on 1 or 2 nodes in the POP, even though the POP may have hundreds of machines. And when a request comes in and it lands on the outer deliver node, that node, the first thing it does is it consistently hashes the request to determine which owner machine is responsible for that object, and then forwards the request to that machine. And so this allows us to scale the size of the cache, so the disk and memory, within one data center linearly just by adding new machines. We don't have to change the architecture at all. But there was a rate of growth, though, and this is what Inez was mentioning about the speed of decision making, that just by adding 1 or 2 more cache nodes wasn't sufficient. We needed to keep up with customer growth and demand. We needed to do it rapidly. So what we realized is if you have nearby POPs in physicality to that data center, maybe inside the same metropolitan region or maybe a cloud region or whatever, we could utilize the capacity of those neighboring POPs to increase the capacity.
Yeah, just have data closer to us, but in a different way.
Right, and scale linearly. And so this is where intersite clustering or metro POPs come in. And so here, if you could imagine in, say, Madrid, we actually had 3 physical data centers. Previously, they had different names. We're now creating a smart abstraction, again, moving that abstraction layer higher, and to a fake POP called the metro POP that now has 3 times the storage of the previous one. But the cool thing here is that each site is still isolated in itself, and it's still designed as if it can function as a single unit. And so every single node in one of these sites here still can take end client traffic, and it's grown the storage by 3x, but still without compromising any of the performance or resilience of the system that the end users connect to us. So each one of these circles still has got its own network capacity, peering, and storage. So if one of these sites were to go down in the metro POP, the whole abstract POP can still function. So we've scaled infinitely while still maintaining resilience, which I think is a really cool byproduct. What makes this design interesting, though, and the specific thing that allows us to scale infinitely, is actually another one of our principles, which is one network, all features everywhere. And this principle dictates that every single feature in our system, every daemon that runs on a machine, every running process, should be on every single POP. And in fact, on every single machine. Every single machine inside every single POP is provisioned in exactly the same way with exactly the same processes running on it. So it allows if one of those to go down, we're just horizontally scaling them. We don't have a tiered architecture where some of the machines are disk heavy, where some of them are CPU heavy for the compute. Every machine is able to do everything, including respond to DNS, respond to HTTP, and logstream. And so by having this principle and by designing it that way that everything is the same, it actually becomes a really simple operation to add whole physical sites to the circle because we've just simplified the design.
It also makes the design easier or simpler to reason about. When you know exactly, you have a level of uniformity, you're able to actually create solutions that are just like easier to reason about. And in a network like ours, like easier to reason about, saves us a lot of time and a lot of grief, and actually makes things easier to debug.
Yeah, and it makes them much easier to operate as well as operators.
Yeah. So everything that you've seen with Patrick mentioning, with all of these graphs and all of these machines and all of these little circles around it, is really, really cool, but it all sounds very complex. And you may not actually have POPs or machines or the use cases that we do. What we really want you to take away is that this is just, again, another example of the power of introducing a smart abstraction in your platform, but it's applied to a different part of a stack. We saw it before, and then we're just going to see this theme repeat a lot. So let me give you another application of the 0-1 infinity principle. And this is how we scaled our TLS certificate capacity. Our initial architecture had a limit of about 3.5 million certificates, which sounds like a lot, right?
Yeah.
Unfortunately, no, Patrick. I'm just here to tell you no all the time, over and over. As you can all guess, 3.5 million certificates didn't get us very far at scale. And why is that? It was because to get certs out to the network, we would generate a single gigantic manifest file, not files, file, on demand that included metadata for all certs in the platform. This file eventually grew so large that it started to become too long to generate, and it placed stress everywhere. The databases, the network, the memory, everywhere. You may have a version of this problem in your platform today, as it's a pattern that is very easy to, and it's very common to follow. You just go and generate a single file. So as you can tell, this wouldn't work for long because, again, it's a singleton that we're trying to vertically scale, and then I've already told you that that eventually just runs out. That strategy doesn't pan out for too long. So what did we do, Patrick, to solve this problem?
Right, and it's a fixed number of items, and therefore it's not adhering to the principle of being able to scale infinitely. So it's actually quite a fun problem to have, although it's a painful one when your customers are demanding more and more. The first thing we did was to break up that single manifest file into many, right, into shards. And so now we would shard this TLS certificate based on its IP address. But the problem is that there's a fixed number of IP addresses that Fastly announces to the public internet. And this worked well. At least it allowed us to start scaling and breaking down and deliver faster. It actually caused hotspotting into the shards and head-of-line blocking. Because if we assigned one of our larger customers that say hundreds of thousands of certs to one of those IPs or one of the shards, that meant that that shard took much longer to compile and process than some of the other shards. And if you were unfortunate to be in the shard behind that, that was now blocking the delivery of your cert while we were processing this one. And so to get around that, we started to brute force the configuration, the compilation of those larger shards. And we would do that by pushing the process async offline and recompiling them every 5 minutes. And so while that worked, it allowed us to scale. It didn't solve the need of infinite, because there's a finite number of IP addresses. And it also, actually, the worst thing, caused friction for our customers, because it slowed down the TLS config delivery, because we were now processing them every 5 minutes in the background job. And so if you were stuck behind that, it was bad, but also now customers were complaining to us that when they added a new cert, it didn't propagate on the network for 5 to 10 minutes.
Yeah, it took too long.
So once again, much like with HTTP caching, we reached for consistent hashing to solve this problem. And so now instead of sharding based on the IP address, we just we hash on the host name of the certificate. This allows us to have any number of shards that we can configure. Right now, we've got about 2,000 shards on the network, but we know that that number we can keep on adding. The hash algorithm changes just to even out the distribution. And because we're hashing on the host name instead of an IP, we get a much more even distribution across all the shards. We no longer get that hotspotting and head-of-line blocking. The other really cool side effect of doing this, though, is that now a shard or an edge machine, and we've got thousands and thousands of them around the world, only needs to fetch a new shard if the data in that has changed, not the full collection every minute. And so what we didn't realize, this also led to a significant reduction in fleet resource wins, a reduction in bandwidth, disk I/O of storing them, and overall faster rollout times for the experience of our customer. When you add a cert now to the network, it propagates in under a minute. And so we've been able to now scale the platform from that 3.5 million to we have today tens and tens of millions of TLS certs are being served on the network today. But we know because of this architecture and the principle of 0-1 infinity, this design is going to allow us to scale linearly and infinitely. And hopefully, touch wood, never have to think about them again.
And the neat thing about this example is that you saw how we started with 1, because it was a single manifest, and then we went to infinity with many hops in the middle, and then we did it as we started to encounter problems, as customers started to notice friction and delays getting their certs out. So that's also something that I want you to take away with this. Again, you don't have to go from 1 to infinity right away, but you can do this incrementally as you go along and encounter problems. All right, so this is all very nice, but let me take you to a different side of the stack. So we've seen things that Patrick mentioned that is mostly in the network and then closer to the edge. But here's another example of when we had 1, but we also needed many. And this is our control panel. The Fastly control panel used to be a monolithic single-page web application, and this was becoming a real bottleneck for our product velocity. It was really hard. It was hard to maintain, hard to change, and it was really, really hard for teams to ship new products. What we needed was a system which would allow internal teams to own their destiny and evolve their UIs independently, but still provide a common user experience.
So it's really common in the back end, we've been doing it for 5 to 10 years in the industry, of breaking down monoliths into microservices. And so what if we could apply that same thinking to your large monolithic UIs? And this is where there's a new trend in the industry of micro front-end architectures. And this is exactly the tool that we reach for to allow us to scale infinitely here. And at the core of the new system that we built is a JavaScript compute application that runs on our edge network. And the responsibility of that system is to compile all of the subcomponents. Each one of these could be their own self-contained React applications that an independent team that don't even know each other or are interacting with each other. And it compiles them at the edge together into a seamless user experience and delivers the base HTML to the client. So the system in the middle of that is this edge system that reads the versions for each component and each one of the fragments from our data store at the edge, compiles that page, and delivers it.
So here, let me use my little pointer thing. I'm like a cat now. I'm obsessed with this. You can see in here that you have a component for the account information, billing support. You see the component that deals with the map and also like your real-time stats. And then list of services, we have a universal nav bar, and this is like the universal search component.
And
oops, sorry.
Using compute to do this at the edge rather than the server allows the team to use the language that they want all the way through the lifecycle of the request. Because compute supports JavaScript, our front-end teams can own their own destiny. They can run JavaScript on the server, the edge, and the client, and actually reuse the same component isomorphically across that. And this has been a significant boost in productivity for us because we're actually reducing the amount of code that we need to write because it can run in all 3 locations. The important thing here is that we've created a system that is disguised as a single UX, but actually is infinity, because we know that this platform will allow us to scale as more and more products and more teams are adding for this. We've created an enabling technology, a platform-level component, which is a big theme of this talk, always be thinking in platforms.
Yeah.
So hopefully we don't have to think about this type of architecture for a while, because teams can bolt on, and we've got the base platform that allows them to ship their product as fast as possible to the market.
Yeah, so that is pretty cool. All right. How's everyone doing? Ooh, OK, great. Let's discuss another principle. So we still seem to have the stamina. So let me give you our final architectural principle of the day. This is build Fastly with Fastly. And what do we mean by that? We mean build the platform with the platform. As you saw in the examples, we have a lot of themes of these things that we reach for this, that was already part of the platform. And this is why we're doing this. This is why we're following this pattern. It means that whenever we build new systems, we try our best to construct them by composing existing platform components that are built for availability and scale. The more we pull and the more people using these components, also the better the component gets, because you start to be able to have more internal use cases, and you actually have like teams that can evolve them with a different perspective in mind. So none of this should be very novel to us, because Patrick has been showing example after example after example of this pattern. But let's dig in a little bit and then just tell you how we build the platform with the platform. This is a great principle again. And as you can see, with every principle that we have, it is really like a true north. But we face some challenges when trying to implement them. So at scale, we have a certain amount of pain with this principle. And why is that so? You have to deal with dependencies. Anytime you choose to leverage a component, and we're telling you to leverage a lot of components and we want to do this, you introduce a dependency, and you have to manage your system's dependencies well. More importantly, you want to avoid introducing circular dependencies in a distributed system, especially if it couples their failure domains. What do I mean by this? I mean that if you have a system A that depends on system B, but B is refactored, so it cannot operate with a system A being available, when A fails, B will also fail, and we have coupled them together, making the platform less resilient as a whole. So dependencies are tricky, and you have to be really thoughtful about them. Another thing that you want to do is that you want to manage your system dependencies well. I have already told you how can it be complicated, but building things faster by leveraging existing components is really good. Building the platform with the platform gives you a lot of development speed. But building faster is not necessarily better if it leads to a fragmented user experience. Friction in your user experience makes your platform harder to adopt, operate, reason about platforms is very important. And more importantly, it makes your platform harder to onboard to. Some of you may have this problem, especially if you find yourselves in larger organizations, participate in events like acquisitions, have independent teams that do not partner well and then want to do it on their own, or if your organization favors development speed over anything else. So it's a tricky thing to do. So Patrick, how do we build a platform with a platform better?
So first, I'm going to actually start with an example where I think that we got this principle very, very wrong. And actually, it's I think one of the most important points to take away is that while your principles are good in principle, don't listen to them too much all the time, or you'll dig yourselves into holes. And so where we got this wrong of building the platform is with our API architecture. And so we front api.fastly.com, the main API that all of our customers use to interact with the platform, and so do we to configure the platform with an edge service. So we could take advantage of all the platform benefits that we give us. And then behind that, we had a shield POP that was running on its own dedicated hardware that wasn't part of the public network, called the control POP, that protected our API origins. And this acts just like the shield that I mentioned earlier. The problem with this, though, is that just because it was treated as every other POP on the network, it was also configured via the same API. What we hadn't realized is that we'd created a tight coupling and a circular dependency between our systems. Because if it meant that if we needed to reconfigure the API because there was a bug in it, or if the control POP went down, or there was a bug in that, how would we do that? Because we needed to make a request through it to fix it. It's a circular dependency, right? And the solution actually was not to listen to our principle. Our principle told us that we should build Fastly with Fastly, and one network, all features everywhere. This should be the same as that. But actually, that's a tight coupling that was bad. And so the solution was to actually completely take the control POP away and have an out-of-band gateway that was out of our physical network completely, so that we could always use it even if the public network was down or the API was down.
So in this instance, we chose not to build the platform with the platform because it actually coupled the failure domains, and we ran them separate. So we did it to follow actually a resilience, which is more important for us too.
And you can see how the principles are at tension with each other here.
I just realized that also we have done this once before, too, when we were building ImageOpto, and we tried to do the same approach, and we had to pull it out as well. So we made this mistake twice.
You need to learn from your failures.
Yeah, we have to.
So a perfect example of where we've got this right, though, is with our new next-gen WAF product. At the heart of NG-WAF is an introspection agent, or the rules agent. And this is the thing that's responsible for listening to the rules, listening to signals, determining whether or not there's an anomaly, a bad actor, or you're under attack, and will block the request. And the agent can be deployed on-prem, in your cloud, or on the Fastly network. And because the agent was originally written in Go, in Golang, and Go is one of the target languages that we support on the compute platform to compile to WebAssembly, we were easily able to compile the existing agent to run on top of our platform. And so the magic here is actually how we composed an entire new product on top of existing platform primitives. The more primitives you build, that actually there's a rate of velocity that increases because you can start piecing the Lego pieces together. So we now run the inspection agent on the edge, compiled to WebAssembly, just as if it was any other customer service running on the platform. The agent is then constantly streaming the request signals out of it via our log streaming pipeline, as you saw earlier, into a Kafka and a Kinesis platform that we own centrally. And then the analysis pipeline is querying that Elasticsearch to detect the anomalies and see, right, it looks like there is an attack happening. We need to change the rule to tell the edge agent to block that thing. It writes that rule change via our normal public APIs to the config stores that customers can use on the platform. So the next time a request comes in, the edge agent will read the new rule, and it knows it needs to block that request and do that. We've composed a whole new product just out of primitives, which I think is really cool.
Again, as Patrick noticed, this composability thing is really, really cool. And then it also allows us to dramatically reduce our time to market. So it has another very real benefit, is that we were able to do this really fast. But unfortunately, this is an example where we didn't take this principle far enough, this principle of building the platform with the platform. Patrick showed us the backend services for NGWAF and showed us how we architected them and composed them. But unfortunately here, NGWAF's UI was still using a UI that was separate from the Fastly console that I showed you before. And this is because it was a leftover UI from an acquisition. This led to a very disjointed and jarring user experience. So it felt like you were hopping from one company to another when you were trying to use NGWAF. Patrick liked to have our cake and eat it too, unless you didn't know about us. And we want both, a faster go-to-market and a seamless UI. So what did we do? We spent the year extending the platform integration of NGWAF all the way up to the UI by leveraging the micro-frontend architecture that Patrick showed us before. This effort eliminates common sources of UI confusion and makes the system easier to use, onboard into, and more importantly, it makes the engineers building this application and building this system have less of a hard time, or just have a seamless way to evolve it and scale it. For me, as we start having these examples, it's hopefully you understand now that it's just this is a true power of thinking in platforms. When you start doing new things with the existing components that you have and you combine them in novel ways and do things that you sometimes just you didn't even know that they were possible. So,
ABTP.
Huh?
ABTP.
ABTP. Yeah. All right. So let's start bringing all of this together, and then just let's summarize everything that we showed you before. We show you things that are very specific to us, and we hope that the patterns or even the mistakes that we made are relevant to you, or they can be applied to versions of these problems in your organizations. So if you were to take one thing away from this talk, let it be these three things and these three lessons. We want you to introduce smart abstraction when you need them, especially if they avoid customer friction. We want you to think about scale in a way that is iterative and intentionally, and you want to be very careful about your resource assumptions, baking in any sort of many or a specific number off. And also, we want you to be careful about your dependencies, how you manage them, and how you think about them. Again, the thing that we hope you take away is ABTP. There's a benefit to always be thinking in platforms, and you want to be able to have design primitives that can be composed easily, and this applies to both backend and frontend. As you saw before in the examples, we were very focused on making sure that the backend reused a lot, and then we actually brought this continuation all the way to the frontend. Another thing that we want you to take away is that it's really helpful to have a guidance strategy and principles to help you make architectural decisions.
So hopefully you've seen that scaling isn't easy. And at Fastly, we can't compromise on scale. That's the one thing we truly agree with internally. And so hopefully giving you this talk has given you some insight into how we approach scaling and building the platform, and that it's a continuous and incremental, as we've seen in some of those examples, effort to leverage our principles to improve the platform, both for customers, internal users of the platform, and external. We've showed you things such as our architecture principles that are well-written, well-thought out, but philosophically well-intended, but they become challenging at scale, and they start to have tension with each other. And it's important to note that they are also living principles. You should always be evaluating them. What you decide today and write down, which you probably should, and have a strategy and learn from your lessons and start drawing things, might not be, though, what you need tomorrow. You need to constantly be evaluating, learning, and adapting.
Yeah, and because we also showed you how easy it is to make mistakes when you're putting these principles in practice. You cannot just blindly follow them without having that reasoning or just like questioning yourself if that moment is the right moment to apply them or not.
Yeah, and we hope that we've sparked some interest in the principles and maybe some ideas in your head of what your principles should be for yourselves. Maybe you've got some as well, and that would be great, and I'd love to hear them, and how they relate to how you build your systems. Because while these are our principles, they may not fit with you. There's some good examples that are universally transferable, but some of them are unique as well, and you need to think about your own and have them. And so
yeah, and there's a lot of
hear.
value in you having your own. Yeah. Thank you for listening to the things that Patrick and I spend a lot of time thinking about. We're going to be around for the rest of the day. Muchas gracias por escucharnos y que disfruten de la conferencia.
Hey, so just a couple of quick questions because we're running out of time. One is about, well, it's Fastly terminology, but some people were confused. So the POP thing is point of presence, right?
Yeah, sorry. I was
center.
meant to say that when I first introduced them. So think of it as a data center. But yes, the specific terminology is point of presence. So Fastly has over 120 globally distributed data centers all around the world, so it's why many people use content delivery networks so that you're closer to the edge. And yes, that's what POP meant.
Yeah, I mean, maybe they are not customers, so maybe your customer supporting might help them. All right, then some people are asking, like, if you can disclose a bit, how do you do the load balancing within a POP?
Yeah, that's a great question. We don't believe in really expensive hardware switches. All of our load balancing is done using software-defined networking. So we actually run switches that allow us to run our own software on it that operates on the packet. And that is aware of the number of nodes in the POP, and will do hashing on the node. It also does health checking at the switch level for all of the nodes in the POP. There's a system called FailD. We wrote a research paper about it.
There's a lot of talks also that we
have.
Yeah,
there's a lot of talks about that.
And so about that. Yeah.
It's switch-based, software-defined load balancing.
Yeah.
Switch-based, okay. All right, this maybe not from your teams, but people are asking, it's more about the UI aspect of things. So once the platform grows and you have more and more services, how do you keep coherence between, what is displayed in terms of like the UI that customers see?
We reuse components. We use the same approach where we have like standardized ways of like the colors, like the design components, and then we just combine them together. So a team can go and spin up their own version of the UI. We will blend it together, but they have to conform to a seamless user experience. Again, we don't want to have this thing where one system or one product feels completely different to the other. And that has been actually like really difficult to keep chipping away and doing it. And then now where we're on this train, there's a lot of like utility and there's a lot of things. Like, for example, I showed you the map. We don't have to create 20 different versions of visualizing a map. That is very jarring if you jump from here to like NGWAF, for example, and see different versions of a map. So we've standardized the map components and we share it across all the teams that need a map. So that's an example.
All right, and a final one. I'm not sure if you disclosed it. Which tool are you using to integrate the micro frontend within the infrastructure? Like, I guess to deploy it or? Well, sometimes the questions are not super specific.
What was the question?
Yeah, which tool are you using to integrate the micro frontend?
At the infrastructure level. Yeah, it's just normal because it's deployed to our compute platform, so it's the normal APIs and build processes that we have to deploy that. You can compile, in continuous integration, we compile a JavaScript bundle that we then deploy to the edge that then gets deployed globally.
And you can do the same thing too using the same tools that we have. So we're just using what is available in the platform. Yeah. We don't use a special version for us. We just reach for the same components.
All right. Well, that covers most of it. Thank you very much, guys. Thanks for coming to Barcelona. Inés, especially, come from far away.
Thank you for listening.